Okay, so the next step in this whole process is to take what we've learned and solve some exponential equations. And we're going to do this with two approaches. One of them will require logarithms and one of them will not. So I just want to jump in here. So we're going to solve some exponential equations and kind of talk about our first approach. So this is approach number 1. And we're going to call this finding a common base. So we're going to be given an exponential equation, and we want to solve it by trying to create common bases on both sides of the equation. And where this comes from is, let's kind of just look at sort of an easy example to start here. So if I gave you an equation that looked like this, 2 to the 2x power equals 2 to the 7 power. So what we should notice about that is that we have bases that are the same on both sides of the equation, right? Our 2 is the same base on both sides. Well, if we have 2 raised to some power equal to 2 raised to some power, what that really tells us is that these powers have to be equal to each other. So I'm just going to write that up here. Okay, the powers must be equal. Or exponents, I guess. Must be equal if the bases are the same. So we're kind of taking a sort of easy one to start with and really dissecting what this is telling us. So then once we know that the bases are the same, then the exponents must be equal. To set up an equation, we just take the exponents and set them equal to each other. And really what we're trying to solve is what x value would make 2x the same as 7, right? That's our goal there. So as far as solving this, you can divide both sides by 2, and you get x equals 7/2. If you haven't already figured out yet, I prefer fractions to decimals whenever possible, so I can get a fraction here. 7/2 is a nice number. I could call it 3.5 because that's an exact value, but I still prefer the fraction. So the goal would be if we can get the bases to be the same, then the exponents have to be equal. So that's what we mean when we say finding a common base. So what if we had something like, maybe where if we look at the equation, the bases aren't the same to begin with. So maybe something like 25 to the x power equals 125 to the 5x minus 2 power. So now my bases are not the same. But my goal would be to try to force the issue, to try to make it so the bases are the same. We've got a number of ways that we could do this. What you want to do, though, is you want to find some number raised to a power that would give you both 25 and 125. So you're looking for a number that's smaller than 25, smaller and or equal to 25, and smaller or equal to 125. Basically, we want to make our bases get smaller, not larger. That's the key. So look for a smaller base that you could use there. So when you see 25, is there any number raised to a power that you know would give you 25? 5 squared, right? So I could rewrite 25 as 5 squared. Now, when we're done with this, we'll talk about another way we could have done this. But what I have is 25 raised to the x power. So this is 25. It needs to be raised to the x power. Okay. Then if we use 5 on the left side, we want to use 5 on the right side. So we have to think about what number, what power of 5 would give us 125. Cubed. Good. So I can rewrite 125 as 5 cubed. And again, 125 is raised to the 5x minus 2 power. So I have to make sure I include that as well. So all I've done is I've taken the bases and I've changed them to something that it allows me to get the same base on both sides. Now, technically, no, that's good. That's good. We're going to leave it there. So let's finish solving this equation. Now, when we have a power being raised to a power, which is what we have here, we have 5 squared raised to the second power. What are you supposed to do with these exponents? Which operation? Add, subtract, multiply, divide. Multiply, right? So we're going to multiply those powers together. So that would give me 5 to the 2x power is equal to, now we could multiply this all out, but I'm just going to write it as 5 to the 3 times the quantity of 5x minus 2 power. Okay, I'm just going to multiply the exponents together. And now we're kind of right back in that situation we were with that first example, because my bases are the same, which indicates that the powers must be the same. So since the bases are same, these powers must be the same. Okay, so I know that those exponents have to be equal, so that allows me to find a way then to set up an equation that I can actually solve. So I could say 2x equals 3 times 5x minus 2. And then I've got just a regular old linear equation that I can solve. I'll have to do a little bit of distributing there. So 2x equals 15x minus 6. But I don't think anybody would have too much trouble solving this equation. So we could subtract 2x from both sides. We could subtract 15x from both sides. It doesn't really matter. I'll go ahead and subtract 15x from both sides. And I get negative 13x equals negative 6. And then divide by negative 13. And I'll get x equals 6/13. Again, I prefer fractions to decimals, because that decimal is going to need to be rounded, and anytime you have to round, it's not exact. So that gives me an exact value. So when we say finding common bases, we want the bases to be the same. So that's the goal. So let's try one that maybe is a little trickier. We're just going to jump right in here with both feet. All right. So our last example in this, and then we're actually going to use kind of what we get to in a certain point in this process to talk about the second approach. So this kind of looks a little scary. So we have 3 times 1 over 121. The 1 over 121 is raised to the 3x plus 4 power. Plus 7 equals 4,000. Okay, my ultimate goal here is to try to get this guy by itself. Okay, if I can get the 121 raised to the 3x plus 4 power by itself, then I can start thinking about how to write common bases. So if this, what I've highlighted, was our variable, we'd have 3 times that variable plus 7 equals 4,000. Well, to solve for that variable, I would just start by subtracting 7. I have 3 times 1 over 121 raised to the 3x plus 4 power equals 3993. And then again, if what I'm trying to get by itself, if my first little goal here is to get this thing by itself, then what would I do next? How do you get that by itself? If we're multiplying it by 3, how do we undo multiplying? Divide. Yeah, so I'm going to divide both sides by 3. What I end up with is 1 over 121 raised to the 3x plus 4 power equals 1331. Now, I'm going to put a little star here, because we're going to come back to that exact place in our process, and we're going to look at how we can solve this with a logarithm. Okay? But we're going to finish solving by finding common bases. Now, if you're finding common bases, you need both sides to be a number raised to a power, and that number has to be the same. So when I look at 121, to me, that screams 11 squared. Okay? So I could write this, and I'm going to do this in 2 steps. You could do it in 1 step. I'm going to write that as 1 over 11 squared. So if I'm using 11 as a base, 1331, if you play around with 11 as your base, you'll soon discover that 11 cubed is actually 1331. Now, we would like to be able to go straight to setting the exponents equal to each other, but we have a big problem here. Because the right side is 11 cubed. The left side is 1 over 11 squared. So we need to be able to write that as 11 raised to some power. Do you remember what type of power would give you a reciprocal of a number? There's a special kind of power that does that. It is negative, yes. So if I wanted to flip that and make it 11 raised to some power instead of 1 over 11 raised to some power, I could write this as 11 to the negative 2 power. Negative powers give you reciprocals. Okay, so if you need a base to move from the top of a fraction or to the bottom or vice versa, you can use a negative power to help you do that. Well, now I've got it in a better form. I've got my bases the same. I'm going to go ahead and multiply that negative 2. I'm going to rewrite it like this. You don't have to do this step if you don't want to. I just like to do it because it makes the powers look a little bit easier to digest. But now I've got the same base on both sides, 11, which means that my exponents have to be equal. Okay, so those exponents have to be the same. And that gives you your equation. So negative 2 times 3x plus 4 equals 3. Now we've got an equation that we should be able to solve. Distribute, add 8, and divide by negative 6. Okay, that part of it should be pretty quick. Once you get rid of the powers, then the rest of it just becomes usually a nice, relatively easy equation, sometimes linear, sometimes quadratic, that you should be able to solve for x. So what I want to do is I want to take that starred step, and I'm going to use that from that point on to solve using logarithms. So our second approach, so this will be approach number 2. Is to use logarithms. One of the most important things about logarithms that you will have to ever use is the very first thing we talked about when we said that log base b of a equals c is equivalent to b to the c power equals a. Okay, that is the most important thing about logarithms. If there's one thing that you remember, that should be it. So we're going to use that a lot because what we're going to be doing is we're going to be taking it from a power into a logarithm. So that's what we're going to be doing. When I say use logarithms, I'm talking about going in that direction, going from a power to a logarithm. And then we're going to need our technology. Graph and calculator usually is what I'd like to use here. So let me take, let me rewrite that. It was 1 over 121. Okay, so we had this. So we'll just call this example 2. And we're going to pick up where we left off after the star there. So 1 over 121 to the 3x plus 4 power equals 1331. That's where I started and said I want to pick up right here. All right, so I want to be able to take it from an exponent into a logarithm. So what I have right now is an exponent. And if it helps, you know, you can kind of highlight the things that you know, like your base b, that's this. Your power c, that's this. A is this. That's your exponent. So then when you start rewriting it, you just have to put the right numbers in the right places. Okay? So if I rewrite this, it's going to be the log. My base is 1 over 121. That seems a little strange. Okay? But it's okay. My power is 3x plus 4. I always think about that's what the logarithm is going to be equal to. And then whatever's left goes here. 1331. So we end up with this expression. Log with a base of 1 over 121 of 1331 equals 3x plus 4. Now comes the part where you need to use your calculator. So if you have a graphing calculator, get that out, because I'm going to have you check for something, and then if you don't have something on your calculator, you'll be able to use a different approach. All right, so when you look at your graphing calculator, I want you to look for math. So on the upper left-hand side of your graphing calculator, there's a key that says math. If you press that, okay, so in the math menu, there's across the top of the screen, there's 3 options, or 4 options, I think. The very first one is math. So if you stay in the math option, so math, and then either scroll, you can do it one of 2 ways. You can press the arrow key either up a couple of times or down a bunch of times. If you press it up a couple of times, there may be an option that says A, and then it'll look like this. I think it says A. Okay. And again, it depends on the software that's on your calculator. If you see that, so when you go into the math menu and you stay in that very first menu, press the up arrow and you see something that says log base. Even if it's not option A, that's okay, as long as it says log base. When you press that, what you're going to see on your screen is this. And it'll give you an option to enter those in. Now, if you don't see that, I'm going to talk about what to do with that in just a second. But if you do see that, very quick and easy way to enter your logarithm. If you don't see it, so if you don't have that option, so we're trying to evaluate log, let's do an easier one here to start, log base 3 of 5, okay? To enter that in, if you don't have the log base option, you will have to type in log of 5 divided by log of 3. Now, the log button, that's what this is. This is the log button on your calculator. Okay, so you should be able to find that log button. It's on the left-hand side of your calculator. I think it's right next to the 7. So you would press log, and then you'll enter in 5, close parentheses, divided by log, enter in 3, and close parentheses. And then that's another way to evaluate it. So the shortcut for that is, and this may be something, if you don't have your own calculator, or if you know your calculator doesn't have the option of using a log base, you might want to write this down. So log base B of A can be evaluated by doing the log of A divided by the log of B. So again, just depending on what version of software your calculator has, you might need that. So depending on the version you have, I want us to evaluate what's here. So either you can go to log base, type in 1 over 121 as your base and 1331 is what's in your logarithm, or if you have a calculator that doesn't allow that, you can just type in log and then 1 over 121 in parentheses divided by log of 1331. So I'll write that here because for some of you, you'll have to do this.
Was it B over A?
B over, A over B. Log base A divided by log base B.
But isn't the base 1 over 21?
Oh, yeah. I see what you're saying. Yes, I wrote that backwards, didn't I? Thank you. You were telling me I was doing it wrong. Yes, I was. Gotcha. Thank you. Okay, what do you get when you enter that in?
-1.5.
-1.5. Anybody else get something different? Negative 1.5. Interest. Okay. All right, so negative 1.5. I was expecting a different value because I did this a little bit differently in the other class. So let's divide, or sorry, let's subtract both sides, subtract 4 from both sides. We get negative 5.5. And then divide by 3. Now, negative 5.5 is the same thing as saying negative 11 halves. So you could say negative 11 halves divided by 3 is going to get you that negative 11 over 6. But if we didn't recognize that, what is negative 5.5 divided by 3? Do you guys write that down by any chance? Okay, so negative 1.833 repeating equals x. If you go back up to what we had up here, negative 11 over 6, if you divide those, you're going to get negative 1.83333. Okay, so it's just another way of finding it. The first way allows us to get a nice, clean, fractional answer, but it's not always possible to do the first way. Go ahead. What happens when we can't rewrite it using common bases? Like, that's just not an option. So we're going to continue to kind of explore writing using logarithms to help us rewrite. So let's say I give you something like this. 4 times e to the 3x plus 1 power equals 622. Now, I would hope that you guys would agree, since our base is e, and in order to use our first approach, we have to have something with a base of e on the other side. I don't know about you, but trying to figure out what power of e is going to give me 622 is not an easy feat. Okay? So we're going to use this idea of rewriting this as a logarithm. But the first few steps remain the same. I still want to get the part of my problem that's being raised to a power. I want to isolate that first. So in order to do so, I'm going to have to divide by 4 here. Okay, I've got to get that e raised to the 3x plus 1 power by itself. That's my first kind of order of business. I can't rewrite this using a logarithm if I've got that multiplier out in front of my base. So when I divide both sides by 4, I'm just going to leave it as 622 over 4. I mean, you're welcome to write it as a decimal if you want. It's not entirely necessary, because in a minute we're going to use our calculators. Okay, so now I'm going to rewrite this as a logarithm. So rewrite as a logarithm. Because there's no way I can find out what power of e is going to give me 622 over 4. Okay, I can't do that. At least not easily. But when I rewrite it as a logarithm, I'll write it as a log with a base of what? So what's the base of my exponent? E. That's the base of my logarithm. Yes, I'm going to come to that in just a second. You're absolutely right. So log base e, and then I always write what my power is over on the other side of the logarithm, because my logarithm's always equal to a power. And then 622 over 4 is what I'm finding the log of. And then yes, we should by now recognize that log base e, that is natural log. And that is important to recognize because that's going to affect how you evaluate. So I'm going to write that as the natural log of 622 over 4 equals 3x plus 1. Okay, now, regardless of whether you have that option in your calculator under math, everybody will evaluate this the same way. So you're not going to go in and choose log base and then put in e as your base. We're just going to use the natural log button that's on your calculator. Underneath your log button, there's a natural log button. It says just ln. So if you press that, type in 622 over 4. Somebody read me what you got to like 5 or 6 decimal places.
5.04664.
Okay, that'll work. Equals 3x plus 4, or equals 3x plus 1. Do you guys all agree with that? Okay. So again, we just did a natural log of 622 over 4, and we get that number. Now we have to solve for x. Okay, that was just the evaluation piece. We got to figure out what x is. So to do so, this is just a regular old linear equation. I can subtract 1 from both sides. And then I'm going to divide by 3. This is when you'll need your calculator again. And I'm going to use an approximation symbol since we are approximating. What do you get? And give me another like 5 decimal places again.
1.34888.
Go one more.
That's all we need.
Okay, 1.3488. Okay, so let's say I wanted to...
It's 3/8.
Oh, it's 3/8. Got
Yeah,
it. Perfect.
sorry.
Okay, no, that's great. Let's say I wanted to round this to 3 decimal places. And I know most of you can round. This is not something I need to go through, but every now and then we've just have a little brain freeze and forget how to round. So let's say I want my final answer to have 3 decimal places. So I want it to go to here. I need to look at the number right after the last place that I want in mind. So I look at this number. If it's 5 or bigger, this number gets rounded up. If it's less than 5, then we leave this as 8. So since it's 5 or bigger, I'm going to round that up to 1.349. I think on the Go Formative, I have you rounding to 2 decimal places. So in this case, if we were rounding this to do 2 decimal places, it would be 1.35. Okay. Okay. I think that kind of gives you the idea of what you're going to be doing here, but I want to give you a little teaser for tomorrow because we'll answer some questions on the homeworks tomorrow, and I want to talk about just this one problem. And maybe you figure it out before tomorrow, and if you do, that's awesome. I may have you share what you got. But this is sort of our teaser for tomorrow. What if we have exponents on both sides? And there's not really a way for us to write these with the same base. Okay, there's not the same number that I can raise to a power and get 5 and then raise to a different power and get 12. So I can't find a common base, at least not real easily. And it might be tricky to rewrite this as a logarithm because you have 2 exponents. So I want you to think about this. And then we'll talk about it tomorrow as well as answer some questions tomorrow.